let's talk about curl. So, what is curl? Well, curl is some measurement of local rotation in a vector field. So, if you had this imaginary vector field, this represents some function, and you found the cross product between the del operator and that vector field, and you plugged in some point. Let's plug in for the point, I don't know, this looks like negative 2, this looks like a negative 2, 2. So you plug in for the point negative 2, 2 inside of that cross product. Well, you would get some positive number here because you are going counterclockwise. So if you had a particle, let's say a water molecule, and you were to have this vector field represent the velocity of that water molecule, this water molecule will go in circles in a counterclockwise direction. And if you were to put, and if you were to find the curl at this point, let's say this is 0, 2, the curl would be negative because you are going clockwise. So, a positive curl represents clockwise movement, and a negative curl represents clockwise movement, sorry. It's going to be a little bit different for three-dimensional vector fields, but this is the general idea for a two-dimensional vector field, and I'm going to show you how to solve for curl in three-dimensional vector fields and also two-dimensional vector fields. For two-dimensional curl, the only thing that matters is the z component. So when you do a cross product, you get a vector back. But for a two-dimensional curl, the only component that will be non-zero inside of your vector will be the z component. So you're actually going to have some measurement of positive or negative. In 3 dimensions, it's a little bit different, but I'm going to show you a general formula for how to solve for the curl in a two-dimensional vector field. So let's say the vector field is defined by P and Q. So the vector field is defined by P and Q. And if you want to find the curl, you want to find the cross product between your vector field and your del operator. So how do you do that? Well, let's go set up the matrix. So the matrix of a cross product looks like so. So you have I and J and K representing your components. And the del operator is comprised of a list of partial derivatives, x, y, and z. And if you have a two-dimensional vector field, you have P and Q, but what is your z component of this? Well, technically, your z component of your vector field is just 0. So it would be 0 here. Now, if you were to find the cross product of all this, so let's go ahead and find the cross product. And if you don't know how to find cross product by now, I have a video on that, so you can go watch that. And there's plenty of videos out there on the internet to learn how to do that, but I'll just go by quickly. So when you're solving for the I component, you cross off this row and this column, and you just find the cross product between this 2x2 matrix, or the determinant of this 2x2 matrix. The determinant is the partial of 0 minus the z partial of q. Notice how q doesn't have a variable of z. This is just dependent on x and y. Comma, actually we need more space, comma, so cross this out. Now you have a 2x2 matrix, comma, the z partial of p minus the x partial of 0, comma, and then we cross off this row and this column. Well, this column and this row. And then you basically find the determinant of this 2x2 matrix. So you multiply by the x partial of q and the minus the y partial of p. And if you were to understand all this, well, the y partial of 0 is just 0. This vector field doesn't have any z components. This is just dependent on x and y. So any partials related to z will just equal 0. Any partial related to z again are equal to 0, and the partial derivative of 0 with respect to x partial of 0 is just 0. So the only thing that matters is the z component. And if you were to simplify all this, you would get 0, 0, and the actual last component that matters is your z component. It's going to be the only non-zero, possibly could be 0, but the only non-zero component. And if you get a negative value for this z component, then your curl is going in a clockwise direction, as I said in the beginning of the video. And if you go into the positive direction, then if the curl is positive, then your curl is going in the counterclockwise direction. And sometimes there could be points of 0 curl. That just means that there's absolutely no rotation going on there. But let's move on to some problems in 3 dimensions to show you how to solve for those. Now, it's going to be pretty important to learn how to solve for the curl because of Green's theorem, Stokes' theorem. You're going to be using curl a lot to solve for anything related to circulation. But let's just start on with this problem. So the curl is just a cross product between del operator and your vector field. So we're finding the cross product of this using this matrix. So we have our x partial, our y partial, and our z partial, and p, q, r. And let's just name the functions p, q, and r, corresponding to each component of your vector field. And to find the cross product of this, all we have to do is look at your first component, I, cross this out, and just find the determinant of this matrix. That's your first component. So the determinant of that matrix is the y partial of r. So the y partial of r, and let's just solve that along the way actually instead of writing it down. The y partial of r is just 0. R is not dependent on y. Minus the z partial of q. So z partial of q is xy plus 2z. How about for j? Let's cross this out and find the determinant of this matrix here. Now I do a little bit differently. I multiply from the top right to the bottom left first so I don't have to worry about any negative symbols. So we find the z partial of p first. So the z partial of p is just 0. And the x partial of r minus the x partial of r is negative z, which is actually just z sine of x. And then lastly, we're solving for the z component of your vector and vector of your curl. So you cross off this row and this column, and we find the x partial of q. So the x partial of q, which is yz minus the p partial of y. The y partial of p, sorry. So that's x cubed cosine of y. And if you were to simplify all this, you get negative xy minus 2z, comma, negative z sine x, comma, yz minus x cubed cosine of y. So this function right here, if you were to plug in any point in x, y, or z, it's going to give you a vector that points in some direction related to the curl. Now, it's going to be a little different because there's no negatives or positives in this case. There's no necessarily counterclockwise or clockwise rotation in 3D. But you don't have to worry about that when you're solving your problems. Let's go ahead and solve for this curl. So this is a new vector field that I wrote down. And we do our cross product again. So you cross off everything here, and we solve for the determinant of this matrix. So we found the y partial of r. So the y partial of r is simply x squared minus the z partial of q. So z partial of q is, again, x squared. And next, we find the determinant of this matrix, because we're solving for our j hat component of our vector field. So we find the z partial of p. Z partial of p is 2xy, and the x partial of r is the x partial of r is 2xy minus 2xy. You can kind of already see where this is going. And so we're solving for the k hat component, so we're solving for this determinant of this matrix. Xq, so the x partial of q is 2xz, and the y partial of p is just 2xz. Therefore, all these cancel out. Just a subtraction of themselves. So you get the zero identity vector. What does this mean? Well, that means that this vector field is conservative. So you can apply your fundamental theorem. The first part, I think. I don't remember the parts. It doesn't matter. But you can solve for the circulation using your potential function. So that means if the curl is 0, that means this is conservative. Therefore, it has a potential function. So let me just add a little bit more nuance to this. Even though there's no actual spinning going on inside your vector field, you can still have curl. So this vector field is represented by y comma 0. And if you were to find the curl of this, so the only curl that matters is the z component. So let's just write down the z component of this. So this is the x partial of q minus the y partial of p. You would find that this all equals to -1. And why does it equal to -1 at every single point on this graph? Well, if you have some point, let's say you plug in 0 here, which the curl is always -1 everywhere. If you were to plug in 0, you would see that there's kind of more rotation going this way and rotation going here. Let's actually write this down. There's rotation going this way. There's rotation going this way. And you know, maybe if you exclude these arrows here that make the actual clockwise or counterclockwise motion. Wait, this is clockwise motion, yeah. Clockwise motion. Then technically, this still has kind of a clockwise motion. So, -1 makes sense in context of this problem because the overall rotation is sort of clockwise, just without any upward or downward movement.